So we'll go ahead and get started. So as I mentioned, my name is Sneha Ayyagari, and I'll be representing RMI. And I really enjoyed working on this project with Emily Higbee from Redwood Energy. And today we'll be talking a little bit more about discussing hours of safety as a framework for understanding the resilience of buildings in extreme weather events. Next slide, please. So today we're going to continue the discussion on the implications of extreme weather events from the last presentation. That was a really great deep dive. And we will talk about defining hours of safety and how this concept can be applied to energy efficiency markets and describe our analysis and potential work. Next slide, please. So I won't harp on this too much since we heard a lot about it in the last presentation, but we're seeing heat waves and cold snaps happening much more frequently across the country, and this trend will only increase in time. NRDC projects that deaths due to extreme weather will increase in the next century if current levels of CO2 emissions persist. And we haven't had many extreme storms yet this year, but this past winter, in many regions, we're struggling with many polar vortexes. And last year, as temperatures plunged in the Midwest down to negative 31 degrees, at least 21 people died, and many more were affected by frostbite and hypothermia. So extreme temperatures are really a year-round problem, and there's just many examples of that. Next slide, please. So with extreme weather, power outages can worsen the risks that are experienced. So when the power goes out, which often happens in situations with extreme temperatures, the problems become dramatically larger. In 2016, some states' power outages averaged between 8 and 20 hours, and that's the average, so many could last much longer, several days potentially. And this is between January and June of 2019, almost 3 million customers were out of power as a result of severe weather. And extreme temperature is a major problem for vulnerable populations, as was mentioned in the last presentation, which includes lower income households in addition to the elderly, children, people with medical conditions, and people living in social isolation. And this is made worse by the fact that low-income housing is often poorly insulated and drafty. Next slide, please. As these outages are becoming increasingly more common, the key question becomes, how can a home maintain a safe internal temperature in a power outage that's caused by an extreme weather event? And this is called hours of safety, which this presentation is an attempt to start thinking about that and lay out some future work to help define that better. So the difference between 5 hours of safety in a comfortable home versus 20 could be the difference between life or death for especially vulnerable populations. And it could allow people to stave off negative health effects such as hypothermia until the power is returned, and allow people to shelter in place and buy precious time for family or neighbors to come and arrive and provide support. And while there has been a lot of work to define resilience of the electricity grid, there's been less work that's been done on how long buildings are able to maintain healthy temperature levels. So hours of safety is a framework that's just as relevant in hot weather events as well as in cold weather events. And we decided to first start focusing on cold weather events because there's a larger delta T between the indoor and outdoor temperature. And while this is an important consideration for everyone, it's especially important when we're considering our most vulnerable communities. Next slide, please. So hours of safety could improve public safety, and it could also unlock more interest and investment in home performance. It can help quantify the value proposition for how tighter building envelopes can both potentially increase energy cost savings as well as improve resilience. And policymakers can plan for public health or safety resilience plans. And so FEMA dollars can be leveraged to improve energy efficiency as a disaster mitigation effort. A 2018 study from the National Institute of Building Sciences found that for every $1 spent on prevention, that can save society up to $6 in emergency response. And so understanding hours of safety can help contribute to this disaster resilience planning by providing another data point that policymakers and decision makers can use. And they can also figure out how to identify neighborhoods that are especially in risk. And we've had a few conversations already with state agencies that have showed interest in further developing this or implementing it eventually. And hours of safety from the consumer perspective can help simplify certain concepts and help them make informed decisions. Currently, many homeowners, as many of you might experience as well in cold climates, purchase gas or diesel backup generators to survive grid outages, but these are often costly and inefficient and can fail without notice. So providing clear, actionable insight on resilience benefit of envelope improvements and providing programs that support that and make sure that that's affordable can help many homeowners avoid the cost of a generator and can also have climate benefits. And the industry can use hours of safety potentially as a way to build their businesses and align with city and consumer resilience goals in addition to climate goals. Next slide, please. So the problem is that the industry does not currently consider the envelope aspects of resilience. And while we usually talk about resilience, we're often talking about things like islandable solar PV systems or battery storage or microgrids. And these are all really valuable and very ideal to have because they can really help keep systems going, especially in disaster situations. But leaving out the envelope considerations leaves out a large chunk of homes and improvements that we could make. And as was mentioned in the last presentation, a similar concept is passive survivability, which is a building's ability to maintain livable conditions when sources such as electricity, water, or heating fuel are cut off. So considering hours of safety can help also connect to this concept. And as we all know, there's many passive design strategies that can be used to improve resilience. And while this isn't surprising, it's a problem that it's not quantified or valued currently in the market to reflect this. Next slide, please. So the market mechanisms, as you know, it is to collect information about building performance are still quite fragmented. We have many different sources, including audits, commissioning processes, utility programs, weatherization of programs, and each of them has a different set of metrics, different methodologies, different types of tests that they do. And so it can be hard for the customer or for policymakers to know how to interpret and use this information to judge the resilience of their home, either on a home scale or on a neighborhood scale. So hours of safety could be a metric that can help put some of these processes and streamline them into a simple and maybe more actionable term. Next slide, please. And in doing this kind of analysis, we first were trying to quantify the impacts of cold stress, and we found that researching the thresholds of safety in cold weather was actually quite difficult, in some ways even more challenging than in hot weather, and Emily can speak more to this, because there's many factors that impact the severity of exposure to cold. And some of these include age and gender, existing health conditions, as well as situational factors such as length of exposure, extent, prior experience with cold weather, and amount of clothing. And we found that there's many health impacts that affect people disproportionately. And however, we note that it's difficult to quantify what that would be across an entire population. And for example, looking at the ASHRAE fundamental graphic here, you see that there's many different types of physiological changes that happen, but they may vary based on who we're talking about. So further work is needed to establish definitively which temperature ranges are unsafe. But we had a starting point from reviewing many different sources. And now I'll turn it over to Emily to discuss our modeling and results.
Yeah, so To understand the opportunity of what improvements could be made to existing homes, we modeled 5 types of single-family homes meant to represent the range of the existing building stock. The 5 models range from no insulation to very high levels of insulation, with high-performing windows and low changes per hour. We also looked at those measures. The models in general represent a typical 1950s home, typical 1980s home with slightly more insulation, a 2009 IECC code home, a zero net energy ready home, and a passive house home, which was based on a Minnesota case study. The geometry chosen for the models mimics a previous study from RMI, and that's shown in the figure to the right. We chose Duluth, Minnesota as a location and a historical year of 2017 weather file to model these homes. And then we simulated a power outage between December 24th and 30th when temperatures were lowest in this year. So as we expected, homes with the lowest amounts of insulation present the most risk. This graph shows zone temperature for each model over the simulated power outage, which was a total of 7 days. During this time, the average outdoor temperature was -7 and getting into the lows of -20 at night. The horizontal line show decided less than 60 was mild, less than 50 was moderate, and less than 40 was severe. The dashed line shows an upper limit of 64 degrees, which was a number that came up and we referenced in the literature for cold stress. One of those references was the World Health Organization defined 64 degrees as a well-balanced indoor temperature to protect the health of the general populations during the cold season. For vulnerable populations, some of the literature suggests a recommended temperature of around 70 degrees. Some building codes do require a minimum temperature, like for the state of Minnesota and the city of New York. They require that homes must be kept at 68 degrees during the cold season. So considering all this, we chose to go with an overall lower temperature scale to represent general healthy populations and as indicators of potential cold stress as opposed to just comfort. If we look a little closely, a little bit closer, looking at the hours, the 1950s model reached 40 degrees in less than half a day, or 8 hours, and was below 20 degrees in about 1 day, about 24 hours. The 1980s model reached 40 degrees in about a day, or 23 hours. The 2009 IECC code home reached 40 degrees in less than 2 days, or 45 hours. The zero net energy ready home reached 40 degrees in a day and a half. And the passive house performed the best by far, staying above 40 degrees for 152 hours, or a little bit more than 6 days. Again, just looking at that data in a different way, this is showing the total hours of the power outage for each model type. The 50s model with no insulation had almost no hours in the safe categories and almost all hours in the severe category. For the passive model, had almost all hours that were within safe to moderate. Between the 1950s model and the passive house, there was a 90% decrease in severe hours. All models were under a day for keeping the indoor temperatures above 60 degrees, which was at the lower end of our scale. The passive house model stayed above 64 degrees for 5 hours and above 60 degrees for a little bit more than half a day, or 18 hours. This figure shows the average measures were providing the most hours of safety. And each line represents the different temperature thresholds. You can see that the passive house model just barely meets the threshold of 60 degrees in 20 hours. With all the measures we looked at, more measures we could analyze, like orientation and window to wall ratios and other iterations like that. to improve the overall safety. Some things to consider further after the study, thinking about questions, things to look into further. What should be the required hours of safety during the power outage events? Shown on the graph is the average length of a power outage we mentioned earlier. This should at least be a starting point at 20 hours. And again, this brings up the question when temperature represents a safe but maybe not as comfortable temperature for all. For example, in Michigan, just last year in December of 2019, due to gas shortages, utilities asked residents to reduce their thermostat temperatures to 65 and to 62 if they're away from their homes. And then also things to consider are the trade-offs between hours of safety and cost. What measures increase the hours of safety the most? What's the most cost-effective strategy? And then further analysis and model iteration can help answer these questions. And now I'm gonna send it back to Sneha.
Thank you, Emily. So as you can see, hours of safety is one metric that can be used to provide more transparency and data to homeowners, the performance contracting industry, and policymakers. And it can be used to identify what are areas where retrofits or in new construction could significantly enhance the quality of the building stock and also the quality of life in disasters. So this increased data availability can also be driven by the private real estate sector in mortgage underwriting algorithms, and this can help insurance agencies potentially mitigate risks. And two possible mechanisms for this could include automated energy models or incorporating it into home energy score or other types of metrics. And this type of information can enable cities to drive more energy efficiency upgrades through local policies such as residential energy disclosure, which would require sellers or landlords to make home energy performance information available to prospective buyers or renters and make that a factor in them choosing whether they want to live there or not. Next slide, please. So this is an initial exploration to set the context for why this idea matters and how it could be potentially influential in the market. So we encourage others in the industry, others that are interested, to also participate in these next steps, which include further researching and developing thresholds for unsafe temperatures and working with healthcare professionals or insurance companies to validate these. And we also, the next step would be to perform energy modeling and regression analysis for both hot weather and cold weather scenarios to determine which of these building characteristics can be used to accurately predict approximate hours of safety. And as Emily mentioned, we would also want to consider cost in making this metric and also in considering the implications of it. And another important factor to consider would be characteristics that would be easy to measure, and we would make sure that we are reasonable in what types of data we would expect to be collected and how that would be applied in this sort of modeling once it's applied in a real context. And based on this analysis, one could create a standardized metric that the industry could adopt and craft guidelines into the ways that it can be applied in the ways that we discussed earlier.
May I ask, in the previous presentation that Tom and Emily did, they were examining the heat waves.
Right.
And Emily, you did some modeling of various interventions, and it seems like you did more analysis of passive house in this cold extremes research than you did on the hot extremes, or correct me if I'm wrong. Did you look at passive house?
The strategy, how we approached the modeling was a little bit different for the cold. For the cold analysis, we kind of looked at five case studies where in the heat stress, we kind of had the optimization component. So we use like the optimized results from BOPT to create our iteration on the models. But those same models could be applied to heat stress as well that I used for the cold stress climate.
Well, to your point, I'm wondering if the standard, and I am ambivalent about saying this, but just to put it out there, if passive house might be that standard, it seems to be its design intent. for it to be resilient in the face of outside climate extremes. And,
Yeah.
So, but I guess that's what I was wondering is, Emily, would you agree that the passive house, I mean, seeing how successful it was in your work right here for cold extremes, does it have that kind of success in heat extremes? Particularly because I hear that passive houses have, that's their main problem, is they have an air conditioning load because of internal heat gain.
Yeah, I mean, I'd be curious to look into that further, but, in California, there's a potential of overheating, definitely. So, what's the balance between the cold and the hot climates, more and more insulation might be better to address cold stress, but that might not necessarily apply to the overheating.
Okay, sorry, thanks
Yeah.
for letting me interrupt there. And so continue.
Yeah, it's a good question and something that would be interesting to analyze further. Yeah, so I just wanted to conclude by saying that we'll be publishing a short paper that includes more details on this analysis that will be up on the RMI website next week, and we can send out the link to people who are interested. And it's a starting point to be built upon a collaborative effort between policymakers and innovators in the space. And we encourage interested parties to take ownership of these action items and also collaborate and share any ideas that they have. And we look forward to continuing to work more on this. And I also wanted to acknowledge Michael Gartman and Jacob Corviday's contribution to guiding and shaping this work. And it was really great working with Emily as well. And we welcome any questions or any input that anyone has on this call. Thank you.
Awesome. Well, Tom contributed over here on the side here. I'll read this out. He says, regarding dry climates to be determined. In general, passive measures will help reduce overheating, but data is limited. This is on overheating. On this topic of cooling, I just investigate this a little bit. So I think you guys might have seen Li Ling and Peter present on the Vermont work. And you're seeing like R40 walls, for instance.
Yeah, I did not see their presentations.
Well, they're recorded and they'll be posted online. That's the good news. So anyone will be able to check them out. It'll take us a week or two. And we're going to be prioritizing Danny Tam's presentation yesterday on central domestic hot water by popular demand. But that said, so they were doing like R40 walls. I'm not sure what your passive house wall was, if you know offhand sort of that metric.
Was 60.
Yeah, looks like I see what you're saying here.
One of the places in the United States.
Oh, Duluth? Super cold spot.
Yeah.
Yeah.
Yeah. Like these were values from a case study too.
Yeah, but I see what, like, it's R55 walls. That's a thick wall.
And then like almost, R95 in the attic. So it was very insulated.
Duluth, I'm from Wisconsin, and Duluth is so much colder than anything I had to deal with. It's what's called politely butt cold. It's so cold there. I know passive house changes for every climate. So just looking at this, as you're thinking about your next steps, like, Sneha, are you publishing this? How does this get expanded further for us to deal with, as you pointed out at the beginning, the lethality of polar vortexes, and of course all the stress, like the sickness and the discomfort, the whole levels above mortality. What do you see as sort of next steps to bring this forward for people?
Yeah, so going forward a few slides, I think that the next steps are really to define a concrete threshold for what are unsafe temperatures, because as we were looking at the heat stress and we were talking a lot about the discomfort index, and I think in heat that makes a lot of sense. I think in the cold climates, we ended up developing these ranges, but I think that we need to zero in a little bit more on how those are described. And I think that another next step that we would really do is perform more energy modeling and regression analysis and see which of these factors we have hypotheses on which different types of building characteristics from passive house that would be influential, like insulation or window to wall ratio, but seeing which of those would really contribute the most to hours of safety. And based on that analysis, be able to understand based on what type of information is easy to collect and is feasible to collect, understanding how we could package that into a metric that could be used and implemented. And so I think there's still many different levels that we could take this to, and it really depends on the level of interest from the industry and also on who else would be able to contribute and different ideas. And I know Michael's also on this call and he's been very involved in this work as well. So if you have anything else to say, either Michael or Emily, feel free to chime in.
Michael, if you'd like to speak to that, thank you for offering. I've just pushed the button that says allow to talk. So you should be able to, there you are.
You can hear me? All right. Yeah. So just to contextualize, I mean, it was a fun project and I guess thought experiment to work around. I think we don't normally get to get our head this high up in the clouds at RMI. We try to stay a little bit more within, the existing system. But it's exciting to think about. It's going to take a gargantuan effort, but just wanted to call out public safety and public health is really important to a lot of people, and we're actually getting a lot of interest just generally around this topic.
I've often thought, like when my mother-in-law died in the Santa Rosa fires, I had this epiphany that I'm sure lots of people have had when there was a public emergency that actually affected their own family, that, oh, that's what government is for. It's to save our lives. And it's not just for a whole bunch of other things, but like literally at those moments, that's what you want a functional government for. And, like the outrage in Australia over the ineffectiveness of its government, or even the fact that the Syrian civil war began with a mega drought there that sent the farmers into the cities. This is hopefully what government is around for. So I'm not surprised you're seeing public safety as a good way to enter the conversation.
Yeah, absolutely. So we recognize that we need probably several PhD students to run the regression analysis that we're talking about to really get this to a point where it can just be planted right into the industry in the way that we want it to. And it's going to have to be this gargantuan effort. And it's a brand new way of looking at this problem and trying to come up with another way to quantify the value of efficiency and resilience and good high performance design. Something that everyone on this call has been pushing for a really long time. So we're not certain that this is the way the industry is going to move, but yeah, public health and safety is always a good angle for us to attack. I think that's a good general lesson for all of us. It really resonates with some groups that don't always care about climate, don't always care about energy efficiency. So I think that's what we're driving towards, and we're seeing some good preliminary interest. There's a really long way to go, but we're going to keep pushing along and seeing who's interested in this topic and who wants to work together.
Cool. Well, sign us up. Like I know that Emily is not 3 PhD students.
She's close.
She's a hydra. She's got multiple heads. No, so just being a normal human being, but sign us up in the sense of love to help you in whatever ways that we can, because this is, like my dad over in Wisconsin had to flee his home during a polar vortex in 2014 because the propane in his tank froze. It got too thick. The gas wouldn't flow into his home, and that was a problem. And so I had just seen this is a big deal. That these climate extremes can really take a toll on people who are vulnerable, as you point out. Older and less good health. Something just give them a good kick in the shins and can send them down.
Yeah, absolutely. And I mean that polar vortex hit quite a lot of red states. And again, this is just thinking about message generally. There are a lot of people that we need to convince to hold our hands in this energy transition generally. A lot of them don't necessarily care about the climate or energy efficiency in the way that we as energy engineers and analysts usually think about it. And we have to put a lot more thought into these alternative storylines and alternative ways of garnering people's attention, because there are a lot of people that don't care about those things, but sure care if their propane freezes.
Yeah, I was thinking that, you know, right now best practices is often considered to, like if you're rolling out a new heat pump water heater, you're supposed to, according to the VEIC who presented earlier, you know, get them in the hands of the plumbers, like give them their water heaters, give them, you know, like gift them so that they'll adopt these measures into their own lives and thereby become advocates for it once they realize that it really was, as advertised, a better idea. I was thinking, oh, it'd be great if we could go to Congress and we could just do a deep energy retrofit, and all of these congressional folks who would oppose or not support enough of the energy efficiency. We should start there. But anyway, that's just sort of political thought. But yeah, because how do we get a societal-wide change to happen quickly? But well, thank you very much. You know, with that here, is there anything else you'd like to add before I transition?
No, I don't think so. Thank you for holding the conference and for inviting us to speak, and enjoyed hearing the other presentations.